Welcome back to The Explainer. Today, we're taking a cinematic deep dive into the mechanical heart of our modern world. We're getting right into the brilliant physics driving alternating current machines, specifically looking at induced torque and what's known as the chasing effect. Let's get started. So, what invisible force actually drives the world's AC machines? It's really not just electricity flowing through wires. It's actually a dynamic, almost high-stakes mechanical mystery playing out thousands of times a minute inside motors all around us. Really, it's all about magnetic fields locked in this continuous, endless dance. Take a look at this physical blueprint right here. Inside an induction motor, there's literally a high-stakes chase happening right now. See that glowing red vector spinning around the outside? That's our stator field in action. And right behind it, that blue vector, that's the rotor field. Honestly, the entire operation of this machine boils down to the exact relationship between these two glowing arrows.
Now, let's break down our two main players. They're actually quite distinct. On the outside, we've got BS. This is the magnetic field originating from the completely stationary stator circuit. Then, on the inside, we have BR, which is the magnetic field produced by the current flowing right through those rotating rotor windings.
And of course, the mathematical foundation governing exactly how these two fields interact is just a single, beautiful equation. It's the cross-product formula for induced torque, tau equals K times BR cross BS. Basically, this little formula is the true engine driving everything we're looking at today.
Let's pull those math variables back into the real world for a second. Think of torque as just a natural urge. When you hold two magnets close together, they naturally experience this rotational force, a torque that desperately wants to snap them into alignment, north to south. It's an inescapable physical pull. So the really crucial takeaway here is that the sheer magnitude of this rotational force relies on three specific things. It's directly proportional to the strength of the rotor field, the strength of the stator field, and, maybe most importantly, the sine of the angle separating them. Think about it. If they ever perfectly aligned, that angle drops to zero and bam, the turning force would just instantly vanish.
We can actually break this whole continuous operation down into three distinct mechanical phases. Phase 1 is creating the rotating stator field, Phase 2 is the interaction, and Phase 3 is the chase. Let's look at how that plays out.
It all kicks off with Phase 1. By feeding a three-phase set of AC currents, currents equal in magnitude but differing in phase by exactly 120 degrees into the winding, we generate our BS. What this does is create a stator magnetic field of a constant magnitude that physically, continuously rotates around the inner perimeter of the machine. Which brings us right to Phase 2, the interaction. Because that red stator magnetic field is constantly spinning, the blue rotor field, BAR, essentially acts exactly like a compass needle near a moving magnet. It's constantly dragged along, attempting to continuously line up with that spinning red vector.
And here is Phase 3, the chase. As torque constantly pulls the rotor forward to try and align BR with BS, the stator field just doesn't wait around. It relentlessly keeps rotating ahead. So you have this blue vector running incredibly fast, but it can literally never catch up to the red one. Which really leads us to this profound mechanical paradox to wrap up today's explainer. Because the stator field never stops moving, the rotor field can never fully lock into a stationary alignment. Never. Instead, that induced torque continuously forces the rotor shaft to physically chase the rotating stator field forever. And honestly, that eternal, totally unwinnable chase is exactly what powers our modern world. So it makes you wonder, what other hidden paradoxes are driving the technology you rely on every single day? Something to think about. Thanks for tuning in, and I'll see you in the next explainer.